met Christoph met Christoph at the GCC, and comes from Braunschweig, so Marcelo can give more background. I suspect you'll be introducing yourself more, Christoph, but what struck me is that what excellent work is happening in the group around the intelligent use of artificial intelligence. I've seen a lot of dumb use of so-called artificial intelligence, so I was very pleased to see the intelligent use of it, and really has a place in our industry, not replacing intelligence, but supplementing what we can do as humans. And that's what really attracted me to asking you to come and give a seminar. So I think you'll find it really relevant in how we upgrade what we can do. It's a new tool in the toolbox, fantastic tool if well applied, like any tool or capability. So welcome to come and join us. It's over to you, Marcelo.
Okay, yeah, thanks, Malcolm. I definitely, I don't have a whole lot to say about Christoph in the sense of a resume, but I'd like to just mention that he is working towards his PhD in Braunschweig under Carsten Schilde, correct? Which is really a long-time partner of ours, GCC, and so I'm exactly like Malcolm said, that I think from past engagements, you might have seen that us in the GCC, at least most of us, have had some restrictions with big data type of approaches or into artificial intelligence, because they very often they lack the proper respect, I'd say, for the process understanding. And so they sometimes led to obvious outcomes, sometimes they led to unreasonable outcomes. And I think when we saw Christopher's presentation in Blues, we saw that the intelligence was put back into that approach. So that's why we were very impressed and very keen on seeing more details on that and embrace as GCC, because I think the process understanding is critical. But of course, the advanced tools out there can give a nice blending with these later approaches like artificial intelligence, machine learning, and so on. So I think please feel free to introduce yourself in a bit more detail, since Sandra is definitely in a very busy place and Arthur couldn't make it today. So please take the floor, Christoph.
Great, thank you. So as already said, I am Christoph Thon from Technical University of Würzburg in Germany. So I'm in the group of Carsten Schilde for around 5 years, a little less than 5 years. And originally I did primarily computer simulations, so CFD, coupled CFD DEM simulations of mills predominantly. And for some time now, I'm, well, 3 years, a little over 3 years in our group, we went into artificial intelligence in the broadest sense of the word. And we applied, among other things, to milling, but also to other topics. But I have a lot of examples also in the topic of milling. So that's essentially also then the topic what I want to present to you today. So perhaps then I start sharing my screen. I managed to do so. Yeah. Can you all see my screen now?
Yes.
Yeah. Okay. Because this is essentially what I want to talk to you today. So artificial intelligence and comminution. So when I start with that, first perhaps I give a little bit of motivation of why we want to do it, what we can do with it. Because if the main thing that you usually do when you speak about AI are predictive models. So essentially what that means is you have a process, any kind of process, could be a mill, could be aggregation, could be anything, a classification, where you change parameters and then you have some measures which also change. And usually you make experiments or simulations, which are quite demanding. And of course, ideally, what you would like to have is you have these input parameters which you change and can make a good generalized predictions of what would come out of the process, so that essentially you can supplement the experiments. You still need to do them or the simulations, but you can essentially on this basis build a generalized model to make very quick predictions. and accurate predictions. And that can be then, of course, used as a basis for further optimization of processes, as well as process control. So there are different AI techniques where you can use this for optimization and control, specifically evolutionary approaches, for instance, which I will describe to you later, but also things like anomaly detection. So you have nominal process, and the AI can detect that something is wrong with your process. Even before you go to any of this, you can use AI to prepare your data. So essentially an intelligent pre-processing. It could be data extraction or AI to use to identify things which are not relevant to your system. And after the modeling, you can also use different AI techniques to get a deeper mechanistic understanding, which is important, because this is usually one of the big criticisms of AI, that it's a black box. So there are different ways of reverse engineer AI. I will also talk about this. And why do we use AI today and not, let's say, 20, 30 years ago to the extent that we do today? One of the reasons is simply the exponential growth of computing, which you can see here on the right side. So you see here, not Moore's law actually, but the price performance of computing. So actually it starts way before integrated circuits, even with electromechanical circuits, with the first 1890 sensors, where they still had rather mechanical computers. And as you can see, over 120 years, over different paradigms like vacuum tubes and transistors, we have almost over 20 orders of magnitude more computing for the same money today. So that's one of the reasons, but actually it goes beyond that, because just the increase in computing is actually the tiniest impact. So this was a study performed a few years ago on AI, and they looked between 2012 and 2018, how has AI improved? So what can you do with 2018 AI systems in comparison to pure financial scale up with the needs of 2012? And as you can see, hardware improvements, classical Moore's law is tiny fraction. Software improvements are much more important. And then you have things like dedicated hardware, ASICs, application-specific integrated circuits, etc. And if you put all of these things together, you get a factor of 1 million in terms of 6 years of improvement. So this is a big difference. And that's the reason why AI is exploding right now in almost every field, because it gets so much more powerful in very short periods of time. And I've prepared a few topics I wanted to talk about today, which I find particularly interesting in the field of comminution and generally process engineering. I mean, typically we have experimental investigations and simulations. Both of them have their advantages and disadvantages. Some are very labor intensive, like experiments, and can cost a lot. Simulations are sometimes quicker, but they're also not 100% precise. They're still very demanding in terms of computing power, and they take time. What you can use with AI is, for instance, so-called surrogates modules are particularly interesting. Essentially, you have an AI which emulates the simulation, so you can make very quick iterations, which essentially emulate the simulation and can even incorporate experimental data. We have on that basis, for instance, design and optimization, of course. I already mentioned that, for instance, evolutionary approaches, process control, and also predictive modeling. Predictive modeling I already mentioned, which can also then, of course, be linked with mechanistic modeling. And if you either have surrogate or predictive models, the good thing is that now you can do in a very short time frame to essentially do virtual experiments in a large quantity. And of course, that way you get a large leverage on top of the data that you already have. And what you can also do, for instance, is calibration. So use AI for calibration, which is very important, calibration of simulations. And what I've called translation, for instance, you have experimental data and you have simulation data. Simulations are usually not 100% what you get in experiments. You have a small gap usually. If you calibrate very well, this gap is smaller. And what you can do, for instance, is essentially have something like a translator, like Google Translate, to translate experimental results, simulation results into experimental results, for instance. So this is a plethora of things how you can use AI on the basis of data which you still need to get from experiments and simulations. So you can gain leverage, but you cannot completely get rid of experiments and simulations. And first, I now want to give you a brief overlook and understanding of how AI generally works. So there are different methods I already mentioned. The classical method, of course, is neural nets. So you can see this here. Essentially, it's loosely inspired by the brain. What you have here is you have an input layer where the input arrives, process parameters, for instance. And here you have the output parameters, which is, for instance, what you measure in the end in the process. And in between, you have these hidden layers. And that's actually where the modeling takes place. And if you look, you see that all of these neurons are connected by connections, and each connection has a dedicated weight. So if you zoom in into one neuron, what you see is that the inputs of the former layer come in with these individual weights. They are summed up. You have an activation function, for instance, to incorporate nonlinearities into the system. You can add things like threshold below the neuron will not fire, and then an input goes to the next layer. So essentially what you do in AI training is you adapt these weights until you get the correct outputs for the correct inputs. So to sum up, a neural net could be explained as a hierarchical statistical system. And on the right, I hope everyone can see this. On the right here, you can see a good example, I think, of why it's so powerful, because the big advantage of neural nets is they can generalize. So this is from image recognition, face recognition, actually, where on a low level, we recognize simple features like that's a straight line, this is curve, etc. On the basis of such patterns, are there more complex features detected, like that's a specific type of nose, that's a specific type of eye, etc. And on which basis of that, you can then detect specific faces, and finally you get a result like that's a specific person. So this is essentially how the information flow goes through the AI from one layer to the next, and you adapt these weights until you get the correct outputs for your inputs, and you usually test with independent data to make certain that it also generalizes, not just remembers past data. Another technique which we use quite heavily are evolutionary algorithms. This is essentially Darwinian evolution, but applied to a technical problem. So for instance, imagine you have a stirred media mill and you have a goal. For instance, you want to optimize energy efficiency or the product output. So you have different process parameter combinations, candidates of different combinations of process parameters. Some are better, some are worse. And what you now do is you get rid of the worst ones, keep the better ones. You mix them a little bit, like a few of these parameters are exchanged with a few parameters of another candidate of combinations. And you add some random mutations also to get a certain genetic diversity. And then you have a new generation, which is tendentially slightly better than the old one. And if you apply this multiple times, over time, this, via an evolutionary approach, optimizes your process parameters, for instance. And what we also use, and this is relevant later on for the reverse engineering part of neural nets, so to get rid of the black box, is a genetic programming, which is a derivative of a genetic algorithm. Here we have at the core not a linear string, which has a fixed length, but a decision tree. And this decision tree can represent a mathematical equation, like this here is 2 to the power of sinus x, for instance. We apply the very same techniques of mutation and crossover of these trees, and the goal is to, over time, adapt a good fitting empirical formula to start with, for a data foundation. And what we use, for instance, is the free software GPLearn. And there are ways to incorporate physics, etc., into this, but I will come to that a little bit later. So as the last slide on the basics for now, I want to show you the training approach. Classical approach is backpropagation. That's an analytical approach. You have training data. You look how good does the neural network works. You have a loss function. And propagating backwards, you then analytically adapt these weights. That works great if you have a very large data foundation. For small data foundations, however, you very quickly get into an overfitting. And what we did, that's an approach that we developed, we call it genetic reinforcement learning, is we apply the genetic algorithm, which I just discussed, on these weights. So essentially, we have a number of these neural nets, identical architecture, but the weights are different. And then we cross over certain weights, we mutate a few weights, and evaluate them with some independent data. And over time, they get better. And also, we evaluate them finally with some data which not goes into the evolutionary training, just to make certain that there's no overfitting by this system here. So essentially what we found is that this is superior if you have a data foundation which is not so large. You need a little more processing power, but therefore you don't get into this overfitting problem that much. So with that, I would like to give you first examples from the institute here. So this is now on the basis of this approach, a predictive model for a stirred media node. So that comes from a colleague of mine and Christine Böttcher, the data. So we had certain parameters varied, and what we want to predict was the x50 of the particle size. So you can see here the result for independent data, so independent testing data that was not used for training, so it's not overfitting. The particle size which should come out and the prediction. And as you can see, we have an R-square of 0.92, so this is already quite a good result. That was one of the earlier results. Here you see what we also did next. That was essentially a first result to get the complete distribution, where we essentially try to predict the distribution as a heat map, and then we could apply a scatter plot on it. And we also got quite good scatter plots. We later found better ways to do it, but that's essentially the first thing, how we applied it on experimental winding data. Here's now an example where I have a little more connected system. So essentially on the left, you see a typical calibration run, which you always need to do if you want to have an accurate simulation. So essentially you have a physical drum where you have your particles in. In this case, we wanted to get the angles of the beads, so the frictions of the beads, and calibrated the product powder into the beads essentially, so that we only had to simulate the beads. The point is, this is usually a very laborious process where you have to do lots of simulations until you get the very same shape in the simulation as you have in the experiment. And we tried to use AI for that. Another thing which you need for the simulation of your mill is the coefficient of restitution, which you typically gain through a drop weight experiment. So you have this ball which falls from a defined height, and you measure the height, how it jumps back, and the ratio between it. And what we also do here again is we add powder, emulating the impact of the product particles on the beads. So essentially, again, we calibrate the powder into the beads. What you also get from this is a flake in the end, and this is a measure of how much amount of powder is stressed between the grinding beads. Another experimental setup we have at the institute, it was developed here, and Malcolm has something has a larger version of that in Australia, is a breakage tester. We essentially want to find out the breakage function. So you have beads which are stressed essentially between two rows, which emulate the impact of particles, and you can then see how the particle size distribution is after it. And we also try to apply AI for this. And then finally, of course, you have your actual mill simulation, which we use with Rocket EM. This is also important because that's where you get the relative velocity distribution of the colliding beads, which are relevant to get the energies of drop weight test, the height, and in the breakage test. So for each of these things, we actually applied AI. So here first you see it for the calibration run. So typically, as I said, you have the experiment that was done with the granite run from granite tools. You get some angles, and then you perform usually iterative a lot of simulations until you get the same shape. And that's a very long process. So what we did instead is we did some simulations and then trained an AI to essentially say we have certain angles as input together with all the other relevant parameters, and we predict the static and the rolling friction would be required to get these shapes. And you can see on top here for the static friction, the rolling friction result. This is this test data one that I mentioned in this yellow background, and this genetic algorithm, and the completely independent test data two. And essentially what you should see is that these two curves, the black line for the test data and the red line for the prediction, that they should align as much as possible. And you see already it works quite well. So we have here a predictive system to at least shorten this iterative approach on the best case, that we don't need to do it each and every time anymore. So you do it, you get a prediction, then you can evaluated with the simulation, and even if it's not perfect yet, you have a good starting point at least, so you can shrink down this very long iterative process, which you almost always need to do when you do DEM. Here's the second thing, the drop weight test. So you see that here we have the ball, it falls down, and you can measure the ratio of the initial height and the height where it jumps back. You can also measure the flake which is forming. And what we did here is we also made a predictive model to predict essentially the flake height and the restitution coefficient. We first did that material specific, which worked very well, but of course then you have only models for one material. We wanted to have it more general, so we added also the frictions, which I just showed you, as a measure for the friction in powder, and also data on the powder from a ring shear device on the input side. And here you can see both the data, the result for the restitution coefficient as well as for the mass. So you see, essentially you have here a kind of digital twin for this drop weight test experiment, which is quite universal if you make these angle experiments, which you usually do, and ring shear data, which are much easier to perform, quicker to perform than the drop weight test. So this is the second thing. The third experiment that we had was the breakage tester. You see that here. It's a modified a device from Exact, where we only use 2 volts, of course, but we can also measure the torque. We can also measure the force between the rolls. And of course, in the end, we measure the particle size distribution. So essentially, we had here the particle size. This was still material specific. We have the density and we had the restitution as input. And no, we had, that was wrong. We had the gap size, we had the rotational velocity and the initial particle size as input. And we had the force, the torque, and 2 fitting parameters as output. So these 2 fitting parameters, they essentially describe the particle size distribution, which comes out of the mill in the end. And as you can see, for both the force and the torque, we have an R square of 0.92, and the voice, the sound disappears in a minute. That's my coffee machine. So that works quite well. And also you can see here for the 2 fitting parameters that you get a very good fit for the particle size distribution, which you get out of this predictive system. Which brings us finally to the actual simulation with RocketDM. Before I come to the results of that, I want to introduce you to a specific type of neural net, which is quite useful for image recognition and generally the processing of image data, which is called a convolutional net. Because what you have here is you have a so-called pooling layer in between, where you have, let's say here you have a small box where you have 3 pixels, or could also be voxels, which essentially slides over the entire domain. And for instance, you can then get the average weights or max weights. And this is a tool which is very often used in image recognition and can improve the result quite dramatically. And what we did here is essentially predicted a heat map of what we would get from the simulation. So this is also image recognition essentially. So here's the result. We had some process parameters, tip speed, grinding aids, filling degree. And what we predicted was, for independent data, how the heat map would look like for the relative velocities of the colliding beads. So you see here the top view this is an independent simulation, and this is the corresponding prediction. And here you see it from the side view, and you can see already it shows quite good alignment. And if you see the density distribution of the relative velocity, you see you need to zoom in to see the difference. There's a difference, but it's a quite small one. So you still need the simulation to get this predictive model, but then of course you can now press a button and get essentially a large leverage to make a lot of essentially simulation emulations. So now I want to talk to you a little bit about our current or the history of how developed AI at the Institute, because this was the initial approach. Initially, we had just basic neural nets already with kinetic reinforcement learning as our basis, but then we had the problem, it's a black box. So we want to get rid of the black box, and therefore we make a lot of generalized predictions. And with these generalized predictions, we can then break them down by genetic programming to get first empirical formulas. So, which are of course a lot more transparent than just a black box where you can not see into it at all. Of course, it's not mechanistic yet. There are other ways which you can also use to break down the black box, so-called hybrid models or semi-empirical model, semi-parametric models. You see that here, this is, for instance, sometimes also called gray box models. Because you have a black box and a white box, you can use the serial, but you can also use this in parallel. This is how we usually use it. How you do it is you have a known white box system, which is a mechanistic model, for instance, or physical model set. And what the black box does, what the neural net does, is only models the difference between the white box model and reality. So it only compensates what the white box model can handle. And what I will show you, there are some other methods like modular neural nets or combinations. But this parallel hybrid model is really the most promising, I think. And that's how we incorporate it to the next version, which is our current version. We call it HYREN, Hybrid Regression Evolutionary Network. So here you see this hybrid model. We have our black box, which compensates the shortcomings of the white box model. And then we use genetic programming to only break down this black box, which essentially compensates the shortcomings. So, and this, of course, can then be iteratively used to extend the white box model. Ideally, of course, a human looks on these empirical formulas and breaks them down further to get mechanistic models. And then we can iteratively extend this white box modeling through the help of AI. So we are currently on this basis, trying to get more physics and automated way into it. So one thing is we have dimensionality analysis so that all the units are correct. So like, this is not like velocity equals mass or something like that. So that all the units are still correct. We want to use AI to automatically from the start identify mathematical relations between parameters so that we can start with a good set of formulas. And this is perhaps the interesting thing is we want to use an AI to detect in the final equations physical components. So essentially we train on the generated basis of decision trees where we willingly and knowingly infuse certain kinds of equations like kinetic energy, and then we can identify them later on, use this training base as a base to train AIs, dedicated AIs, to actively search for different kinds of equations in these decision trees. So here's another example, which with the very same idea with the heat maps on the case of coupled CFD-DM simulations of the stirred media mill. Again, you can see for different layers that for the prediction for these independent simulations, we got a very good result. But what I showed again is the second part, because here we use genetic programming afterwards to break down the black box. So we made a lot of predictions. It was like 900 predictions. One simulation took like 3 days. So if you would have made these 900 predictions, some of them take even longer if the particles get smaller. Which you have here tip speed and beat diameter as parameters, it would have taken between 1 and 10 years to completely systematically simulate it. But through the limited amount of simulations which we had, essentially to get this was the press of the button. And with this generated database, you can then apply genetic programming to break it down to a most transparent model, an equation, which you see here. We modeled the relative velocity, 99 in this case, independent of the tip speed. So because there's quite a difference between tip speed and relative velocity, you can measure tip speed, but you cannot measure directly that easily relative velocity. But that's actually what's relevant for the winding. So you can get equations to describe these relations with genetic programming. So here's now the next example of surrogate models. So a surrogate model is essentially an AI emulation of a simulation. We did this on the basis of lights. So if you have a simulation, of course, you can simulate large domains, long time spans, but of course there is a limit how long it can be and how large it can be. So what we wanted to do is we have a small scale unit cell where we do a lot of simulations very quickly because it's small. And then we can use this as a training base with initial positions and forces and positions and forces afterwards to predict what will happen to these particles. And the idea is that in the long run, we simply have a large domain, which we may not be able to simulate anymore. We discretize it, and for each of these unit cells, we apply an AI, have new positions and forces, remesh, and apply this iteratively over time, so that essentially we can emulate the simulation via an AI, but much quicker. So that already worked pretty well for a few times. The problem is, even if the error is tiny, if you applied 1,000 times, tiny errors accumulate. So what we tried now was to essentially, on the basis of an initial time step, predict essentially a tracerate. So 4D hypercube, where we have all 3D positions over time as an extra dimension. That worked a lot better. So you see here a compression simulation with DEM for time step 5,600. So it was essentially compressed by a factor of 2, and had very good correlations. You see there are some tiny deviations, but it looked quite good. You see here in the end of the simulation, the correlation here is the simulation, the position in Z direction, so where we compress the largest deviation, and the prediction. And here you see it for the stresses. So that worked already quite well. And the most important thing, of course, is how much faster was it. For that specific case, compression, it was essentially faster by a factor of 3,000 without much improvement in performance, of course. So we can, I think, go beyond that. And right now we try to go to a more complicated case of free particle flow. So essentially we thought of a few case studies where essentially we should capture all patterns of how particles flow in such a system and apply the AI framework on free particle flow, which then could be perhaps applied in the future on milling, etc. So of course it's more complex than just compression. So let's see how this works out. So this is one kind of surrogate model, but there are other surrogate models. This is now not from us, this is from other sources of literature that was applied for CFD, for instance, which you can see here for CFD prediction, but also for upscaling of CFD nets, essentially, to essentially also gain leverage again. And on the right side, you see perhaps the most prominent example. This was protein folding. So Google a few years ago, 3 years ago, essentially solved protein solving because that was a problem which was essentially unsolved for decades, because you couldn't accurately predict, at least not more complex proteins, how these amino acid chains fold into unique three-dimensional shapes. Classically, you do this with MD simulations, but they did it. And a few weeks ago, they released as an open source all 200+ million proteins now to science. So essentially went from 90,000 proteins experimentally investigated to a similarly good folded 200+ million proteins. And of course, you can see this is enormous benefits for drug design, etc. So essentially, you can now do virtual drug design where you do billions of examples on the press of a button, and that brings me back to these virtual experiments which I meant in the beginning. So another thing which you can do is optimization of processes, for instance, or optimizations of geometries. What we try right now is, this is an ongoing project, is we want to, by an evolutionary algorithm, optimize, evolve over time, essentially grow a stirrer of a stirred media mill. So we have a voxel domain where we essentially take a few proportions, make crossover of different candidates, mutate them, and put them in a simulation and run it in a circle that essentially a genetic algorithm improves over time the geometry. So one could say it's a novel approach to essentially with zero knowledge go into a system and derive an optimized stirrer or any kind of machine equipment, essentially to derive this by an evolutionary process. And then, of course, you can make studies. What are the underlying problems properties, what makes it so good, and then you can elaborate on that. I don't have good results to show you on that, so everything works, but we're now introducing it to the simulation. So let's see how this works. But I have another example where we use it, such an approach to optimize particle morphology, because very often you use, for instance, QuickPick to get particle shapes, but of course you only have 2D images, but the particles which you have and which you want to apply in DEM, for instance, are three-dimensional. So you need to get the 3D shape. And what we wanted to do here is to predict, based on the 2D images, the 3D shape. So essentially, we generated a lot of particles artificially and made artificial projections. Like from different angles, we get how they look. And with this training base, we can then essentially train an AI to predict the 3D shape or parameters like flatness and sphericity, etc. So this here is the cross-processing. So you have generated particles, you get images, and you can also get a voxel structure or mesh structure, and then you can use essentially the pixel images or via convolutional net as input, the 2D images, and predict the 3D shape, like the voxels as output. And then you can have some smoothing of the surface and get prediction of the 3D shape. So these are some initial results which we have. So these are independent particles, so not used for training, the initial particle, as well as the predicted shape of the particle. So it's not yet perfect yet, but already reasonably good. So, and what we want to use in the future is another kind of AI to further improve it, which is called a GAN. So it's already reasonably good, but I think we can go even further with the help of a GAN. Which we already used in another context. But first, perhaps at this point, I describe how GANs work, because this is actually a very interesting technique, because you have two AIs working against each other. So it's typically used in image recognition. So whenever you have seen a deep fake, so a person doing something which actually they didn't do, this is usually coming from a GAN. So it's called generative adversarial networks. You already see working against each other. One learns to generate an image based on training data, and then that's the generator. And the second AI, that's the so-called discriminator, he has the task to say, this is real or that's a fake. And one of them wins and one of them loses. And over time, they get better and better because they train each other. So essentially now you can just give on some online tools a small sentence and get an image generated from an AI, which are already reasonably good. And we use that for essentially the example I already showed you a few minutes ago, the calibration run. But what we did this time was not predicting the frictions, but turning it around again. So essentially, we added the frictions as input and particle size, etc. And we wanted to predict the shape, which results in the end. Via a GAN. So we see here the training process. So in the beginning, you just see a fuzzy image. It has no resemblance to calibration run. And over time, it gets better. And in the end, if you then also add the parameters, you get, this is again independent data, the original data, which should come out and a generated image of the calibration run. It's not yet perfect, but already reasonably well. Excuse me. So that already works reasonably well. And as a last outlook, essentially, I want to give you something new which we are trying right now, because everything I showed you today so far is essentially called narrow AI. Because AI right now is still mostly used on the basis of people 60 years ago, when it first was conceptualized in the 60s and 70s. How people back then thought the brain works. And actually, in the meantime, we have learned a little bit more. So if you want to learn more about this, you can, for instance, Google Numenta. That's a company in America. Because how the brain actually works is a little bit different, because it's not this, you have inputs, they're summed up and then they go out like a processor in a feed-forward way. Actually, each neuron is actually on its own right a prediction machine. So you have three kinds of regions, essentially, where they detect patterns. Most of them are outside, too far away from the cell body to make the cell really fire. So only 10% of the synapses make the cell fire, the other 90% cannot. What they do is they detect a pattern which usually predate their own activation. And what then happens is they depolarize the cell body. And if then really this cell gets active, they fire a tiny bit sooner than they otherwise would. And if they fire a tiny bit sooner, they inhibit the other cells which were not predicted. So this is essentially already quite a difference. So essentially that's, it's called HTM, hierarchical temporal memory. So if you look to the brain, to the architecture, actually you can unfold the neocortex. You have tiny columns actually, and that's the unit of intelligence. We have 150,000 of them. So if we just understand this column, which has the size of a grain of rice essentially, then we have understand not just narrow intelligence, but general intelligence. So the ability to take something which we have learned in one context and apply it to another, which classical AI right now cannot do. So this is a lot more complicated than classical AI actually, so I will not go much further into this. Also, I think the time is slowly running out. So as said, I will show you a few first things we have done at the Institute. So this is in the initial stages compared to the more classical AI stuff. What we have done here is essentially, this is not yet process engineering related, just a virtual mouse which runs around to kind of virtual box. And we detect where certain neurons fire. And as you can, because we do know that there are certain neurons in the brain, like cells which only fire in location, or cells which only fire when the mouse looks in a certain direction, cells which fire only at borders, and cells which essentially form a grid over the surface where they navigate. And the interesting thing is most of these things we could already detect. So here we have border cells essentially building a virtual CAD model. Here we have a kind of a swirl, which we don't quite know what it does, and that's the interesting thing. All manner of neurons, all do some very systematic thing, but all different things. And here we form a kind of grid for navigation. So why is this relevant for process engineering, perhaps one day? Because evolution took this approach from navigation and applied it to model n-dimensional abstract parameter spaces. I mean, we all know phase diagrams, for instance. That's a three-dimensional representation of a physical system, which has no real counterpart in physical reality, like a 3D shape or something, but we visualize it as a 3D shape. And the brain does really the same. It builds an n-dimensional model of all manner of things. And we also applied it, and that's the last thing I want to elaborate on this basis for CFD, so kind of CFD surrogate model on this HTM system. So we had a simple 2D CFD where we had some turbulence, etc. And we added a point sensor. And what we want to predict over time is, for instance, the temporal development of pressure or velocities in the system. And just after 50 time steps, it could already very reasonably predict the temporal development of this. So this is, of course, very early stage, but I just wanted to point out that below classical, beyond classical AI and narrow AI, there's also this world of more general AI, which is evolving right now in parallel, which can also be quite interesting for process engineering applications. So with that, I'm at the end of my talk. Perhaps interesting to notice that soon there will be actually a paper on AI in particle technology, so more or less the topic of today. That should come out soon. So with that, I'm at the end of my talk, and perhaps there's still some time for discussion.
Oh, thanks, Christoph. Excellent. Big hand for him for I'd say a 40-minute intensive AI introduction for really advanced topics here. Fantastic, quite exciting. So as we anticipated, when we saw your 15-minute presentation in Toulouse, we saw there's a whole lot more on the background, and thanks a lot for all the details you provided there. I think we have still a few minutes, so we can open the floor to questions and discussions. Please feel free to introduce yourself and pose your question. It could be written or open mic.
Hi, this is Haijie speaking. Hello, really nice presentation, very informative. I kind of have some specific questions. If you go back to the CNN part, convolutional neural networks, I actually have a question there because CNN is usually, as you explained, is usually used for the for image processing or image predictions. So here you basically transferred the numerical simulations into pictures, then use these pictures. Okay, so I see. Then is the heat map you change or you use or the resolutions of the pictures will affect the prediction performance?
So we have the process parameters as input, and we have the heat map as output. So we train with the heat map. So you wanted to ask how much improves the quality of the system, or?
No, I just wonder because the heat map, or there are different ways to represent this this simulation result. Yeah. Will this heat map you generate or some other representatives pictures will change the performance of the predictions?
For instance, we gained these density distributions through the heat maps. So the heat maps are actually intermediary steps. So we do not predict directly the distribution. And that indeed works a lot better if you first have a spatially resolved the complete domain, instead of just making a prediction of either distribution or just an x50 or something, or relative velocity 50 or something.
Yeah, okay. Yeah, interesting. Okay, I have a second question about maybe, I think in slide 16 or 17, I think you have this illustration, basically overview of the framework. Yeah, this specific one. If we go to the right side of the, so basically you want to use the machine learning model and supervise it. So, added some expert knowledge in this field, then feedback to another machine learning model in the AI. So basically you apply 2 machine learning models here, right?
Yeah, so we first have, so of course, on the basis, we have the white box model. So that really dominates the system essentially. So we have something which we understand as foundation, but then we have the first AI model, which is the black box, which is a neural net, which makes a predictive model of the deviation. And once we have this predictive model, we can then break that down with the second approach, the genetic algorithm, to break the black box down to a transparencies, to a set of equations. And actually on that basis, we can apply a third AI model, which I described here, to essentially, let's say, semi-automize this third step here, to identify within these decision trees known mechanistic or physical equations, like, okay, we have a decision tree here which has a very high likelihood that the kinetic energy is involved. And then it essentially can show us here there's most likely the kinetic energy. And that, of course, makes it a lot easier to identify physics within these empirical formulas. We can do a few other things like penalties to let the equations not get too complicated. We want them to become as compact as possible, of course. We don't want an infinitesimally a very large equation, which may be 100% perfect, but completely transparent again. So we can enforce the equations to remain slim. And of course, what we can also do is we can artificially incorporate physical components in the genetic program by initializing with physics in the decision trees. So of course, that way it becomes even easier if there is physics in the data that it's incorporated within the equations.
Okay. Yeah, this part is very interesting because I know it's relatively hard to explain what is behind your machine learning model or AI model. So yeah. So eventually they will come out some sort of short equations, and you're trying to understand what these equations represent. Okay. Yeah, interesting.
Exactly. And you have this iterative approach because let's say you have, for instance, let's say you have an exponential function overlaid by a sinus curve, right? It may be difficult to describe this accurately, but if you have it iteratively and reduce the complexity, first it might just recognize the exponential function, and then it's incorporated in the network model. And if you just then look at the deviation, then it will see the sinus curve, right? So that's another way why it might be useful to keep the formulas slim.
Yeah. Okay. Yeah.
Thanks,
Oh,
Haji.
thank you. I have no more questions right now. Yeah.
Excellent.
Thank you.
Yeah.
So, anyone else, fellas?
Hello, Johannes Christ from Fraunhofer Chalmers Center. I have a question. Thank you for a very nice presentation. I was thinking about this concept called catastrophic interference or catastrophic forgetting. Basically, if you change the system you are modeling to a certain degree, the neural net will collapse. And that is, I think, of relevance when you're in the field of optimization of various kinds of mechanical systems. So could you comment on that and methods to mitigate those effects?
Yeah, that's why it's so, there are certain problems, as I said, this is narrow AI, and that's really the big thing. It's narrow trained on a very narrow problem. If you change the problem, often it breaks down. So there are certain ways of compensating for it. One way is, for instance, use something like a convolutional net or so, which essentially proves over the entire domain you don't have such a fixed structure anymore. Another way is pre-training. Essentially, you have a pre-trained AI, which is trained on a similar data set, but not an identical data set. That could be done simply because you have far more data in a related domain. And then you use this pre-trained AI as a basis for fine-tuning with your real data. Then you essentially save time, but you still need to do this fine-tuning. So you have a finished system essentially, but you have something changing. And then it may make sense to take this last step, but continue to train it on this basis. So pre-training is quite important. And what I think is also an interesting thing here are modular neural nets. So, I mean, you have modular neural net means essentially you have somewhat closed neural nets and you connect them, because that way you also have a certain structure to it which is somehow normalized, right? Because that's the problem with neural nets, the classical neural nets, is you change one weight and you change the complete system. That way you reduce that effect. This is, by the way, one of the advantages of this last kind of general AI, the brain AI. There that doesn't happen, because there you can continue to train and it remembers everything that it has learned in the past. It learns something new, so it doesn't intermingle with old data. But with classical AI, classical neural nets, you need to be careful with that. So there are certain techniques, and I would say modular neural nets is one, pre-training is another way to cope with it, and a way to normalize the structure of it, like convolutional nets or something else.
Excellent, Christoph. Any other questions?
So I have a question, Magnus Evertsson from Chalmers University of Technology. Maybe it was on slide 11. You had the roller crusher and the PSD. Yeah, this slide. If I look at the output here, force and torque, those are normally related to maybe fracture toughness or any other strength type of parameter of the material. And if I look at the input, those are more or less orthogonal to that. How can you predict force from density, for example?
Yeah, I must excuse that. I already corrected it in the talk this was wrong here. So we had actually the gap size, the rotational velocity, and the initial particle size. So these input parameters, these here are wrong.
Okay.
So,
but still, I'm trying to understand the AI here.
Yeah.
You are predicting something, and don't you need information, even if it's a proxy or a meta type of variable? It should be related to something that could, that could in an analytical model give you force.
Yeah.
And because with these parameters you demonstrate here and corrected to, they could still, I can imagine a lot of materials that could have similar density and similar, but they would have different, microstructure, different fracture toughness. Just if you change grain size, but you have the same composition, then you would have a tougher material and higher force and torque. And force and torque, by the way, are probably related to each other. So they are almost the same parameter. So my question is still, how can you predict a parameter where I don't see the content in any sense, like particle size that has very little to do with force?
Yeah, so essentially you're absolutely right, because right now, let's say we had this other example here, and here we also started with material specific models, but then we went to more universal models. So we had parameters like friction or the ring shear data, which essentially characterized the powder. We did not go to that point with the breakage tester. This is still material specific. So we use CPANAT for this. So it's the model right now is only usable for CPANAT. Here we did not yet go to the point where we had it more universal. So you're absolutely right. What we need in addition would be parameters to characterize the powder which goes into it. We have that right now. This is more a predictive model for the machine, for the experiment, but for specific material systems at this point.
I'm still confused about this. And if you use the fall weight test, for example, you could as well have done a fracture toughness test. And then, well, at least in a lot of different types of crushers, force is directly related to fracture toughness.
This is actually a very interesting point, because what we already saw is, essentially we did this here, is that if you have various types of characterization methods, if you have a few of them, you can essentially predict the others. So we had these three here, the calibration one, the ring shear test, and the drop weight test. And we also tried a few other combinations and could make predictions of that. Of course, so essentially, you can essentially replace a few experiments to others, what we learned through that essentially. So we have a digital twin essentially for the drop weight test, because we only now need to do the angle, which we use in any case, and much quicker to apply a ring shear device test. So we can essentially take different types of experiments, and we don't need to perform all of them anymore, because the data is already within others.
Yes, thanks, Christoph. I think we're going over the hour, so maybe I can just make one final quick question, which is, I think some models that we have been developing, like ourselves and you guys in Braunschweig, which use DEM, CFD, and population balance, we are pushing them forward, I think, quite a bit. But the challenge I see is incorporating them into a process simulator. So I know that you guys have been working with process, so in such a way that you want to put your model inside a big circuit. But if the model is very complex, that's a challenge to be able to even iterate and work with closed circuits. So I wonder if, even though you didn't talk here, but I know you have been doing a lot of things on the background, if you are considering implementing some of those models that are very complex into process simulation, using these ideas from AI?
Well, so of course we have this problem with transparency, but we only look at the speed of the model, right? So how long does it take to apply? Then we can also use the AI models, the black boxes, because AI takes a long time in training. But inference, so the application of the trained AI, this is really a press of a button. So this can run in real time.
Okay, excellent. So it looks like maybe there's going to be like a potential coupling of an app that you calibrate outside the complex environment simulator, and then take the learnings into the process simulator to be able to use this complex model alongside with other unit operations, correct? Yeah. That would be a potential. Excellent. Well, we are already over the hour. I don't know if there's still one final question here. If not, So I think we can thank Christoph for the great presentation there and great class for
Thank
us
you.
on the topic. On behalf of the GCC, great work there, and we'll be looking forward to see the upcoming results from your work. So thanks everyone.
Thank you very much.
Thank you.
Thank you very much.